it's a great pleasure to have here Professor Krishna Rajagopal, and he took his PhD in Princeton, then he moved to Harvard, Caltech, and finally went to the MIT. And now he's also the Dean for Digital Learning at MIT. He was also a chair of the faculty. His main research was about quarks, in particular quarks when they are not confined inside hadrons. So when maybe temperature is so high that they are almost free, or in a case in which you have a high heavy collision that reproduce locally the same situation. And to deal this physics, he was at the border of many branches of physics, particle physics, nuclear physics, astrophysics, and he used also technique very sophisticated like the gauge gravity duality, which was invented in string theory. So please, now we will talk about doping and probing the original liquid. This original liquid is precisely this mixed plasma of quark and gluons, which I was alluded before.
Thank you very much. So thank you for the invitation, Fabio, Francesco, and it's a pleasure to visit Padova. An alternative title for my colloquium could be Heavy Ion Collisions, What Next? And I am going to focus on the what next question, but in the first part of the colloquium I have to catch you up on the last 15 years or so of activity in this field. So experimentalists at the Large Hadron Collider and at the Relativistic Heavy Ion Collider in the United States are recreating droplets of the matter that filled the microseconds old universe. And by a combination of experiment and theory that I'm going to walk you through very quickly, very briefly, we now know from about 15 years of effort that what they are producing are little droplets of the first liquid that ever existed, hence the original liquid. This was the liquid that filled the microsecond-old universe. If you go back to earlier times in the universe, the quarks and gluons and muons and electrons and photons were all a weakly interacting plasma, but during this microsecond epoch, they became a strongly correlated, strongly coupled liquid, which is now being produced and studied in these experiments. So this liquid was original in that sense. It was also original in the sense that it is the source of all the protons and neutrons in today's universe. All the first protons and neutrons formed, this liquid fell apart into a mist. This liquid is a few trillion degrees hot, so it's also the hottest liquid that we know of. As far as we know, the hottest that has ever existed. It was the earliest form of complex matter that formed. In a sense that I'll explain more in a few minutes, it is the most liquid that has ever existed. The liquidness of a liquid, to me, is quantified by a certain dimensionless ratio of the shear viscosity to the entropy density, often called the specific viscosity, which for this liquid is 0.1, and I'll put that in context in a bit. And then the other reason why this liquid is interesting there's a sense in which it is the simplest form of complex matter, by which I mean the complex matter that is in some theoretical sense that I don't intend to mean precisely closest to the fundamental degrees of freedom of the standard model. So I will spend the next 10 minutes walking you through how we have come to this picture, but all great discoveries pose new challenges, and the main part of my talk is the what next question. What are the new challenges for the decade to come? And that will be the largest fraction of the talk. So this liquid has a name. It's called quark-gluon plasma. This is its historical name. The name was coined long before the liquid was produced. It's actually a terrible name because it should be called quark-gluon liquid, but it's too late. The reason it's called quark-gluon plasma is that if you take the temperature to infinity limit, you really do get a plasma. You get a fluid of quarks and gluons, and the fact that Qcd is asymptotically free means that if you go to the infinite temperature limit, the interactions between the quarks and gluons are weak, and you will get a weakly coupled gas of quark and gluon quasiparticles. So that's why this phase was named in the way that it was. More recently, lattice calculations of Qcd Thermodynamics, which I'll show on this slide, have shown that if I calculate, for example, the energy density in units of temperature to the fourth, it rises rather dramatically but continuously in this crossover, which you can see blown up here, happening at temperatures of around 150 to 200 MeV. And these energy densities are characteristic of a gas of hadrons. And what is this 1 here on this plot? The units of energy density are plotted here such that 1 means a non-interacting gas of quarks and gluons. You go through the undergraduate textbook counting of degrees of freedom of the quarks and gluons, the non-interacting Bose gas for the gluons, non-interacting Fermi gas for the quarks, add up their energy density as a function of temperature, and that's what this lattice calculation is plotted relative to. And the mistake that everyone made before the experiments began was to say, well, this calculated result is pretty close to 1, so presumably we're going to have, when we get to these temperatures, we're going to have a weakly coupled gas of quarks and gluons. The experiments were then done, and it turns out, as I'll tell you, this stuff here turns out to be a liquid, not a weakly coupled gas at all. We could have guessed this if we were paying very close attention to some early work in string theory in the late 90s. And those of us in the QCD community were not paying attention at that time. Because, well, saying this in more modern language, we now know of a large class of cousins of QCD with dual gravitational descriptions, in which, for all these other theories, if you change the coupling from 0, so very weakly coupled, to infinity, the energy density only changes by a factor of 3/4. So in all these other theories, the infinitely strongly coupled soup is at 0.75 on here, and you'll now notice that actually this is closer to 0.75 than to 1. But the real lesson of this history is that by looking at energy density and pressure and entropy density, you can't tell whether you have a gas or a liquid. You need to do something else to figure out what you have. And so the way this community figured this out came from experiment. This is what happens when you collide 2 gold nuclei at RIC. This is an early RIC collision. Starting in 2010, we had the first lead-lead collisions at the LHC. And summarizing 15 years of experimental work and theoretical analysis of that experimental data, hydrodynamic analyses of RIC data on what? On how little blobs of this stuff expand, and really they expand explosively, so better to think of it as explode, have taught us that the quark-gluon plasma is actually a very strongly coupled liquid with a dimensionless characterization of how much dissipation occurs as this liquid flows and expands, being much smaller than that of all other known liquids. And this is the discovery that makes this soup of interest outside our narrow particle physics community. And I want to explain to you, to give you a sense of how you measure the liquidness of a liquid. And I'm going to do it using a different liquid. This is a different experimental gold. So this is an ultra-cold cloud of fermionic atoms trapped in a trap. And the experimentalists in atomic physics have a trick that they can play where they have a knob to turn where they can make the interaction between these atoms infinitely strong. And this is the experiment that they then do. This is a movie of it, in effect. They trap their cloud of atoms in this cigar-shaped trap, and then they turn off the trap. And now, if this were a gas and you turn off the trapping potential, you turn off the walls that are holding it in, if this were a gas, what happens? If it's a gas, there's a million or 10 million or 100 million atoms in that cloud. They're all going in random directions, and they hardly ever bump into each other. And so they'll just fly apart isotropically. And this cloud will rapidly circularize as it expands. But if this is a liquid, then there are pressure gradients that are much stronger left to right than up to down. And so if this is a liquid, when you turn off the walls, it's going to explode with much greater force left to right than up to down. And if you look at the movie, that's what happens. So this thing explodes left to right much more than it explodes up to down. And that tells you that this is a liquid, not a gas. And when you quantify this, you can quantify from data like this in atomic physics, you can extract the dimensionless measure of how much dissipation occurs, because you see, when this is a liquid, it has some viscosity, and as it's exploding like this, there's shear in the flow, and if there's viscosity, that turns the shear of the flow into heat, dissipation, and heat is random thermal motion. So the more viscosity there is, the less of the sort of pent-up potential energy here gets turned into anisotropic flow, the more isotropic this would be. So you do all this quantitatively, and in atomic physics, you measure the 8/s of this gas, and or this liquid, excuse me, and that's the idea. Now, we're not going to focus on this liquid. I want to focus on quark-gluon plasma. Before I do, though, there's another fly in the ointment, which is when you collide two nuclei, initially you don't have equilibrium. You don't have a droplet of fluid that's been sitting there for a while in a trap. You make it in a collision. So does it equilibrate fast enough? Here also, so if I collide two nuclei, think of two nuclei colliding and think of them colliding off-center. If two nuclei collide off-center, you make a droplet of liquid that's sort of almond-shaped from the intersection of two circles off-center. And if it takes a long time for that to become a liquid, then all the quarks and gluons will flow outwards isotropically before they realize, hey, wait a minute, we should be a liquid. And then it'll be circular before it starts behaving like a liquid. And so the fact that in experiment you see anisotropic final states tells you that equilibration has to happen relatively quickly. And in fact, this was one of the first discoveries at RIC, now 17, 18 years ago. And it's a long-standing estimate that equilibration, or the validity of hydrodynamics in heavy ion collisions, only takes about 1 Fermi over C to happen. And that's incredibly fast, because 1 Fermi over C is the time it takes light to cross a proton. Now, here also, you can ask, in those cousins of QCD in which you had that strongly coupled, infinitely strongly coupled liquid, which you could analyze with these by mapping it onto a gravitational calculation that was easier to do, which gave us that factor of 75% a few minutes ago. Can you study collisions? And the answer is yes. This is a space-time diagram of a collision, not in QCD, but in a cousin of QCD. This is time and space, and one, it's not a nucleus, it's a sort of sheet of energy density comes in from this side, one comes in from that side, they collide, the energy density gets large, and then this is the liquid that's formed in the collision. And you can analyze this quantitatively, as the authors named on the slide did, and they found that equilibration occurs in this collision after about 3 sheet thicknesses in time, which is about here. You study this quantitatively and you find it's behaving hydrodynamically. And that, if you translate that back to RIC, would be about 1/3 of a Fermi. And so maybe equilibration in 1 Fermi is not surprising after all. Okay. So I've given you a very, very quick beginning of a story that has played out really over the past 10 years, and I'm going to now cut to the chase. I'm going to leave out many interesting twists and turns in the road. The message is that by doing hydrodynamic calculations of starting from the initial state of a nucleus-nucleus collision, including the initial lumpiness of it, okay, because lead nuclei are not smooth. They're made of protons and neutrons, so that lumpiness matters. And by looking at the initially lumpy initial conditions, so this is a theorist's conception of the way energy density is deposited when two nuclei collide at early times. So you take this as the initial conditions for hydrodynamics, and then you let these things explode, and you're going to get anisotropic final states. And this is in many ways analogous to the way you analyze the microwave background radiation in cosmology. This is a slight cheat by making this figured like this, because this is actually the final state in cosmology. This is the photons that the experimentalists go and see, and they see an anisotropic final state. And they analyze that by doing Fourier harmonics. And if you look at this, this goes all the way up to Fourier mode 1000, and they get a power spectrum of this, fluctuating final state. And what we do in this field is you do a hydrodynamic calculation. This is the initial state. You let it run. You look at the final state, and you Fourier decompose, and we get 6 Fourier modes. I'm sorry about the projector, but what's plotted here are the second, third, and fourth. The fifth is also measured. The sixth is also measured. but what's plotted here is second, third, fourth, and fifth Fourier moments for particles with a given momentum, and then the hydrodynamic calculations are shown as the lines, and you can see they work quite well for a viscosity of 0.12 at RIC and 0.2 at the LHC. And so from doing this, I shall state the conclusion on the next slide, but in cosmology, the analogy is actually really quite good, because initial state quantum fluctuations, which may come from inflation, they're very interesting, are processed by hydrodynamics in cosmology, and they appear in the data as a fluctuating final state whose Fourier modes you measure. And that tells you about the fluid of cosmology, and it tells you about the initial fluctuations. And it's at this level, it's exactly the same in heavy ion collisions. There's a fluctuating initial state. The protons and neutrons are in different spots in different collisions. Those fluctuations then are processed as this droplet explodes. And at the end of the day, you get a distribution of thousands of particles in your final state, which has fluctuations. You Fourier decompose those, and you learn both about the initial fluctuations and about the properties of fluid. In this case, it's viscosity. Now, cosmologists have a huge advantage because they can look at 1,000 Fourier modes. We only get to look at 6 so far. But we have a huge advantage because we have 1 billion bangs. Cosmologists only get to study 1 big bang. We have 1 billion little bangs. In a typical data set in a heavy ion collision experiment, you have 1 billion collisions on tape. So we have 1 billion little bangs, 6 Fourier modes each. Cosmologists have 1 big bang, 1,000 Fourier modes. Okay, so I've tried to give you a sense of how we get conclusions as are on this slide. So the quark-gluon plasma at RIC, which reaches temperatures up to about 2 times the crossover temperature, has an 8 over s, which is between 1 and 2 in units, where I've multiplied 8 over s by 4 pi here. I wonder why I did that. I'll tell you in a second. At the LHC, higher energy collisions get up to more like 3 times the crossover temperature, and the range of uncertainty for 8 over s is a little bit larger because, again, there's a higher temperature range. I'm being quite conservative here in quoting these ranges. The uncertainty principally in this comes from knowing exactly how to describe the lumpiness of the initial state, and I think many people would tighten this range a little bit, but it doesn't matter for my talk. Now, is this big or small? 4 pi 8 over s equals 1 or 2. Is that big or small? Well, 4 pi 8 over s is 10,000 for the air in this room. Okay? And 4 pi 8 over s is between 10 and 100 for water, liquid nitrogen, liquid helium. Any of the liquids we know in the laboratory have a 4 pi 8 over s that's in the tens or hundreds. And 4 pi 8 over s for that ultra-cold atom fluid whose movie I showed you is more like, it's a little less than 10. It's somewhere between 5 and 10. And so 4 pi 8 over s between 1 and 2 or 1 and 3 makes this liquid the best liquid we know. It has less specific viscosity than any liquid we know, including water. So it's more hydrodynamic than the liquid after which hydrodynamics is named. The reason I quoted it in these units is that all of those gauge theories that I mentioned now for the third time, all of those gauge theories that are cousins of QCD and that have a secret alternative description in terms of a gravitational theory, they all have 4 pi 8 over s equals 1. So this has become the benchmark for specific viscosity, and the quark-gluon plasma is the liquid that we know whose actual measured viscosity is closest to this theoretical benchmark. So why is this interesting? Another way of saying why this is interesting is that with an 8 over s as small as this, there's no way you can describe this liquid as being made of particles that travel some long distance between scatterings. You can't describe this as a particle which propagates and then scatters, propagates and then scatters, propagates and then scatters. Because if you try and do this, you find that if you try to do this, you would compute a mean free path that corresponds to this viscosity, and it will be shorter than the spacing between particles. So it makes no sense. So it's a liquid, it's a liquid, it's a liquid. There are other fluids known in nature that are as strongly correlated as this, including high-temperature superconductors. The electrons in high-temperature superconductors are strongly correlated in the same sense. These are different materials, of course, but in the same sense that it's very hard to find a quasi-particle description. Quantum spin liquids matter at quantum critical points. In all these cases, after you discover a new form of matter like this, what do you want to do? You want to dope it and probe it. And that's where we're going for this colloquium. So having discovered this new form of matter, there are two kinds of what next questions for the coming decade. The first is, what is the phase diagram of this stuff? In condensed matter physics, you map a phase diagram out as a function of temperature and doping. Doping in condensed matter physics means excess of electrons over holes or holes over electrons. We're going to do the same thing, except for us, it'll be an excess of quarks over antiquarks. And then the second what next question, which will be the topic of the third part of the colloquium, is one that we have the privilege to ask because our strongly coupled liquid, the one that nature has given us to study, exists in an asymptotically free gauge theory, which means that if you could find a good enough microscope that you could probe this liquid with very good resolution, you would see that it was made at short distance scales of weakly interacting quarks and gluons. And so we can ask, how do the weakly coupled quarks and gluons at short distances conspire to arrange themselves into a strongly correlated fluid at longer distance scales? And if we can answer this question here, maybe that will help us understand the analog question in other condensed matter physics contexts. Okay, so phase diagram first. For orientation, this is a phase diagram of a condensed matter physics system, a very famous one. This is the sort of cartoon level phase diagram of high temperature superconductivity. And with a color scheme that was chosen on purpose to sort of resemble this one, here's our phase diagram. So for condensed matter physics, temperature on the vertical axis and doping on the horizontal axis, so excess of holes over electrons on the horizontal axis. For us, temperature on the vertical axis and excess of quarks over antiquarks, so doping with baryon number on the horizontal axis. So this is the vacuum. Nuclei or nuclear matter live here. They have a large excess of quarks over antiquarks, and they're at zero temperature. The stuff that was discovered at RIC and the LHC lives up here on the phase diagram. It's very hot, and to a very good approximation, it's equal numbers of quarks and antiquarks. You collide two lead nuclei. This brings in 200 protons and neutrons. This brings in 200 protons and neutrons. When you look at the final state of a collision of the LHC, there's 30,000 pions in the final state. If you just think of that in terms of the excess of quarks over antiquarks, you make so much entropy, so many new particles, that the excess of the doping is very small. And that then tells you how you dope quark-gluon plasma. You do collisions at lower energy. So if you imagine going backwards in history to lower energy collisions, they didn't have enough energy to make 30,000 new particles. Once you get to collisions that are, let's say, these energies here, so these are lower and lower and lower collision energies. Lower collision energies don't explore as high because they don't make as high temperatures. So higher collision energies, higher temperatures. Lower collision energies, lower temperatures. But lower collision energies, these collisions, you collide nuclei at these energies, 200 protons and neutrons, 200 protons and neutrons, you only make several hundred new particles. And that means that the soup that you make is much more doped by the quarks that came in the initial nuclei. So as you go to lower energy collisions, you make a colder droplet of stuff and a more doped droplet of stuff, and then you get to explore this phase diagram. Each of these trajectories means you make a droplet of stuff and it expands and cools and goes downwards on the phase diagram. So every collision corresponds to a trajectory on the phase diagram. The LHC is here on the vertical axis, and going down and down and down to much lower collision energy, you get to explore this region of the phase diagram. I will mention there's interesting things that happen out here. The way to study them is to look inside a neutron star. Neutron stars have densities in their center that are here on the phase diagram. Well, actually, we don't know if they get into here or not, but they're certainly here on the phase diagram. That's a subject for another day. So to map the phase diagram of QCD, that's the question of how does the quark-gluon plasma change as you dope it? And you dope it by making it in lower energy collisions. And there has been a lot of progress in answering this. How does QGP change as you dope it if you don't dope it too much? And I'm going to give you just a sense of this. I will not explain everything in this slide, but some of these things come from experiments, some come from hydrodynamics, and some come from lattice QCD. This is the region of the phase diagram. So this is temperature and doping. So this is no doping, and this is a little bit of doping. And these gray bands come from hydrodynamics. This pink smear comes from lattice. These black points come from experiment, and these colored bands all come from lattice. And the fact that everything crosses nicely is a sign that we know how things work. And the message is that in this yellow smear here, we actually have a pretty good understanding of what happens. And this continuous crossover that I showed you here doesn't change all that much. So this yellow smeared region we understand from a combination of experiment and theory. And the frontier is this region here. The goal for the next decade is to extend our understanding out to this region where there may be a critical point. So notice the question mark. We don't know if this crossover becomes a first order transition, but it might. There are good arguments why it might, but no rigorous calculations. And so one of the goals for the coming decade is to map this region of the phase diagram in an experimental program at RIC that I'm going to tell you a little bit more about. So this is the question of how is that crossover between quark-gluon plasma, this original liquid, and ordinary hadronic matter, how is this crossover affected by doping? Does it turn into a first-order phase transition above a critical point? Now, in principle, we theoretical physicists could answer this without any experiments. If we could do a lattice calculation out here in the phase diagram, lattice calculations with non-zero doping are very difficult. It has to do with the fermion sign problem. For those of you who know it, I won't explain it. On the theory side, we need new lattice technology in quotes. So in a sense, this quest to map this part of the phase diagram is a race between theory and experiment. And I want to talk more about experiment in this colloquium. I will not talk about the kinds of theoretical developments that some are working on. So we're trying to work our way outwards here to lower energy collisions. And exploring the phase diagram is a goal of what the program at RIC called the RIC Beam Energy Scan. There was a first phase of this program with data taken between 2011 and 2014. This was the sort of exploratory phase. The collider ran at these low energies in between doing other things. And got relatively low statistics data sets. And there are very suggestive and interesting and intriguing suggestions of interesting phenomena, including the possibility of a critical point. But all the error bars are very big, and no sharp conclusions can be drawn. And so this provides strong motivation for going back and doing these low energies at high statistics, and that is coming in 2019, next year, and 2020, and 2021. So this is indeed the program for the next 3 years at the Relativistic Heavy Ion Collider in Long Island, New York. So this, again, I think it's your projector. But this is doping, left to right. And these are two different observables as a function of doping, which means as a function of lowering the collision energy. So these are high energy RIC collisions or LHC collisions. These are the lowest energy collisions that have ever been done at RIC. That scans in doping from, if I go back to this slide, it scans in doping from here all the way out to here. So the lowest energy collisions done at RIC freeze out here. It's a reasonable guess to think that they start out there. And what you see in both these observables is relative to a baseline, you see interesting and non-trivial and non-monotonic behavior, but with very large error bars. And I'm only going to tell you about this one. I won't tell you about this one. So I'm going to show you this one again. But let me just say that the data here were taken with this many collisions, as shown in the gray bar, at each energy. So this is 20 GeV, this is 7.7 GeV, and this is a log scale. Let me look on here. This is millions of events. This is 10 million events. This is 100 million events. And what you see is that there were less than 10 million events at this energy. The red bars are the plan for the coming 3 years. So this is, by a factor of 100, more data than was taken before. That's what's coming. And the motivation for that, I'm going to explain, is this curve. And the line is just to guide the eye. The issue is that the error bars are too big to be convinced that there's that this curve really goes down and then up. But if it goes down and then up, that's what's interesting, as I'll now explain. So here's that data again. This time I think you can see it. Look at the red points, and as a function of doping, so again, high energy collisions, undoped plasma, low energy collisions, doped plasma. Okay, so what's plotted? Now I'll tell you. So you do a collision, you pick a certain byte of acceptance, a certain fraction of the collision, and you count the number of protons minus the number of antiprotons. And then you do that 10 million times, and you see how the number of protons minus antiprotons fluctuates. So you have a distribution of that number. It has a mean, it has a width, and it's probably going to be approximately Gaussian. Most distributions are, but not exactly. And so you measure the moments of that distribution, and this is kappa is the fourth moment of that distribution. And one here, it's normalized in such a way that for Poisson fluctuations, you should get 1. So 1 equals boring. Okay? And what you see is that this measure of the non-Gaussianity of these fluctuations first goes below 1 and then goes above 1, but the error bars are bigger than you would like if you want to make definitive statements. So how might you understand this quantity going below 1 and then above 1? Well, it's exactly what you expect at a critical point. How do we know? Well, this critical point, we don't know if there's a critical point there. But if there is, we know a lot, because this is an Ising model critical point, and from condensed matter physics, we know a lot about Ising model critical points. And through a chain of reasoning that is quite reliable, if there's a critical point, we can show that because of its Ising nature, this fourth order cumulant for the number of, it's a proxy for baryon number, but this fourth order cumulant for the distribution of the number of protons is negative in the red region on the phase diagram and positive in the blue region. And remember that as we come down in collision energy, high energy collisions, lower, 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 lower collisions, we should first go negative and then positive relative to the baseline, which is Poisson, which is 1. So if you now go back and use your rose-tinted glasses, which I just gave you, if this first goes negative and then goes positive, it's very hard to find. There are other prosaic explanations of why it might go only negative or why it might go only positive, but no one has suggested any other explanation of it first going negative and then positive than an Ising critical point. And so, you know, the negativeness of this point, if you add these points together and average, it's actually, this is pretty significant, this negativeness. But now you look for the positiveness. These two, their error bars touch 1, and this is maybe 2.5 sigma off 1. So this is not significant. So where we are right now is we have a reasonably convincing demonstration of this observable going negative, by which I mean below 1, and a hint of it going positive. And that's why we need more statistics. So negative contribution of the kurtosis is established. This fourth moment is called the kurtosis of the distribution. And is this a harbinger of the approach to a critical point? The signs of an upturn are encouraging, but we need more statistics. We also need much progress on the theory side. I'm not going to walk you through how you do theoretical analyses of heavy ion collisions, but there is an enormous theoretical effort going on right now involving several dozen theoretical physicists around the world, less than 100, but certainly many dozen, trying to develop the modeling needed to describe the hydrodynamics of these low energy collisions. Everything is harder at low energies, turns out. This is needed if we want to make quantitative predictions. It's all well and good for me to stand here and tell you that Sorry, where's my data slide? It's all well and good for me to stand here and say this should go down and then go up. But if you want quantitative statements as to what you predict from theory to compare against these experiments when their precision gets better, there's a lot of work to be done, which is underway and which I'm not going to describe today. But the idea is that the experimentalists are planning in the next 3 years to get 100 times better statistics, and the theorists need to be ready. So I thought what I would do is show you slides. It wasn't mentioned in the introduction. The reason that I'm passing by Padova is last week was at the Quark Matter conference in Lido di Venezia. This is the big conference in the field. And I will not say I'm going to show you highlights. That's absolutely not true. I'm going to show you, at 2 different points, I'm going to show you new and interesting results from my own collaborators. So it's a completely biased perspective. But this is one of 2 spots where I'll show you something that's fresh. This is from a student of mine, her talk. Her name is Jasmine Brewer. She gave a talk at the conference, and these slides are hers. And this is a small theoretical advance that has nice experimental implications. The idea here is that when you scan the phase diagram, for each collision energy, you can vary the rapidity that you look at. And in a heavy ion collision, the baryon number is not distributed uniformly. It tends to be larger at high rapidity on both sides and less in the middle. And that means that if you scan in rapidity, you can actually have sort of, in this Vernier scan analogy, you can do a fine-grained scan in rapidity at each collision energy. And so to think about this on the phase diagram, this is a diagram like I showed you before. And if I increase the acceptance in rapidity, that's like scanning with, as I increase the byte of rapidity that I look at, I will be averaging over more and more of the phase diagram. And that suggests that instead of just averaging over more and more, maybe we should bin in rapidity. So look at this bin, then this bin, then this bin, then this bin. And this choice of binning in rapidity, Jasmine and her collaborators, which includes me, point out will lead to a more crisp picture of the critical region. And we then made an effort to show this. This is an estimate of where you might be on the phase diagram if you vary the rapidity from 0 to 0.6 to 1.2. And if you bin in rapidity, what you find is that first it goes negative at low rapidities. That's the negativeness here. Then it goes positive at higher rapidities. And this would give you the very interesting fact that the fluctuations increase with increasing rapidity here. But then and that's the same here, but if I then look at a case where I have passed the critical point and I'm now scanning like this, then the fluctuations decrease with rapidity. So this gives you a way to tell which side of the critical point you're on. So this is a new suggestion, and in fact, the experimentalists from RIC are in fact busy trying to figure out whether they can get enough statistics with the plans that I showed you before to slice their data in rapidity and to do this analysis. So that's, that I think is where I am on that, yes. So to end this part of the talk, I hope I've given you a sense of one of the what next questions. How do you dope the plasma? How do you look for interesting phenomena as you do? And in so doing, map the phase diagram of QCD. The next time Francesco invites me back, I should be able to tell you whether there is or isn't a critical point in this region. Of course, all the experimentalists know that theorists are scoundrels. If the experimentalists don't find a critical point in this region, you can bet that there'll be theorists who draw cartoons where the critical point is here. Okay? So you can't oversell this. There's no reliable knowledge of whether the critical point is here or there, but at least RIC is basically somewhere between doubling and tripling the region of the phase diagram that will have been reliably explored. And so let's see how it goes. Invite me back in a few years. It's a 3-year experimental program. Okay, so that was the first what next question. The second what next question is, how does this liquid emerge from an asymptotically free gauge theory? Question I asked in the introduction of the colloquium. So this is about probing the original liquid. Any new condensed matter physics system, you either scatter neutrons off it, or you scatter photons off it, or you scatter electrons off it. You study its structure by shooting something off of it. Same in particle physics. How do we know anything about the structure of the proton? By taking a proton and scattering electrons off it. So we want to, what we would love to do, take a drop of quark-gluon plasma made in CERN, transport it across the Atlantic Ocean, put it in front of the accelerator at Stanford, and shoot electrons at it. That is, of course, impossible. Droplets of quark-gluon plasma live for 10 to the minus 22 seconds. So we'll have to be more clever than that. But I want to, in the second half of the colloquium, talk about how we can probe its structure. The question to ask is, how does the strongly coupled liquid emerge? And emerge is a wonderful word because it has multiple meanings. So let me tell you 3 meanings of the word emerge. First meaning is emerge as a function of resolution scale. When you have a drop of quark-gluon plasma, if you look at it with very, very, very microscopic fine-grained resolution, it does not look like a liquid. It's the weak quarks and gluons. As you coarsen your microscope and look at it on longer scales, the liquidness emerges. That's the meaning that I'm actually going to focus on. That will be most of what I mean when I say emerge. But there's another sense of the word emerge, and that is as a function of time. When you do a collision at time 0 in the collision, it's not a liquid yet. It's just a bunch of quarks and gluons going like this. And they just collided. Not a liquid yet. What are the physical processes that take you from the initial condition, which is very far from being in equilibrium, and turn it into a liquid? That is the second sense of the word emerge. And then the third sense, maybe a bit of a stretch in the use of the word emerge, but in the third sense is, okay, a droplet of liquid this size is a liquid, but what if I make it smaller and smaller and smaller still? What is the smallest possible droplet of liquid? And then if you go the other way, if I make small droplets of stuff and make them bigger, at what point do I see a liquid emerge? Each of these is a very interesting question that animates entire parallel sessions at the conference that I was just at. I could spend an entire hour on any one of these 3 questions. I'm going to focus on the first, but I will say a few words before I do on the third. So what's the smallest possible droplet of liquid? We theorists missed the boat because we should have been asking this question. And any of us who were doing calculations with these cousins of QCD, which had the strongly coupled liquid in it, should have asked what was the smallest possible droplet to which this description applied. We didn't ask it. Any of the hydrodynamic folks who were studying those lumpy initial states and their hydrodynamic evolution could have asked, what's the smallest little lump that behaves hydrodynamically? It was not a theoretical question that was asked. This question was asked by the experimentalists. They did collisions of protons on lead nuclei at LHC and deuterons on gold and helium-3 on gold at RIC. This could be the whole colloquium, but there is a lot of evidence from these collisions of liquid-like behavior when you shoot a proton at a lead nucleus, which makes a very small droplet of stuff. After that evidence came, theorists went and looked at calculations of shooting small objects at big objects in these cousins of QCD, and they found that what you get behaved hydrodynamically as long as its size r times its temperature T was bigger than 1. And if you plug that in, that actually suggests that in proton-lead collisions, because of the size of the proton is what it is, you should get very small droplets of liquid. So this story hangs together. It was a surprise initially, but after the fact, we shouldn't have been surprised. And for today, I'm not going to tell this story with any more than on this slide, but what this tells us is that if we want to study the microscopic structure of the liquid, we're going to have to look at pretty small scales, because this liquid behaves like a liquid on scales of order 1 over its temperature, which is about half a Fermi. So this then is what leads us to jets. We need a microscope that allows us to study the microscopic structure of this liquid, to see its inner workings. We need probes with much finer resolution than half a Fermi. And nature gives us two potential multi-resolution probes. We don't get to bring our droplet of stuff to an accelerator elsewhere. We have to use as probes things that are made in the same collision that makes the stuff. So you collide two nuclei, you make a droplet of liquid, you have to look for collisions where the microscope was made in the same collision. And there's two options that people work on. One are upsilons, which are BB bar mesons, and they're very small. In particular, the 1s state of the BB bar system is smaller than half a Fermi. And the 2s and the 3s are bigger. So these are elementary particles made of bottom and anti-bottom quarks that come in 3 different sizes. And so there's a lot of experimental work on studying their, what are they or are they not bound in the quark-gluon plasma? Do they survive the plasma? And LHC data indicate that the dissociation pattern of these states depends on their binding energy. The small ones survive, the big ones fall apart, are unbound. So that tells us about the screening length of the QGP. It tells us whether, if I have a B and a B bar here, are they attracted to each other, or does the QGP between them screen the attraction? But it doesn't tell us what the QGP is made of, because a liquid can screen your interaction and so can a gas. So this is actually a very interesting domain of the subject, but it does not answer the question that I'm trying to answer. So jets, well, jets are also multi-scale probes in a little bit of a more challenging sense. So what's a jet? I do a heavy ion collision at the LHC, and I make this droplet of soup. In the same collision, I make let's say a quark-antiquark pair with 200 GeV energy each. So very, very high energy quark going this way, antiquark going that way. This is the best that we can do in terms of taking our droplet of soup and bringing it to Stanford and shooting an electron at it. Okay, that's impossible. Instead, we find those events in which there was a 200 GeV quark made in the same collision and study how that 200 GeV quark probes the medium as it shoots through it. Now, what happens to a 200 GeV quark in the absence of any quark-gluon plasma? You don't see quarks in your detector, you see jets. So what happens is that this quark initially has a very, very high momentum, so it probes a very, very short distance scale, but then it starts to shower and fragment and split. Each splitting has a characteristic momentum scale associated with it, and as it splits more and more and more, the characteristic momentum scales get lower and lower, so the resolution scale gets longer and longer. Similarly, you can make the same argument in terms of momentum transfer between these partons in the jet and the soup. So a jet starts out very hard, it ends up made of softer particles, and the way it interacts with the medium starts out harder and ends up softer also. So these objects, or jets, are the best chance that we have to study the inner workings of quark-gluon plasma. They're the closest we'll ever come to doing a scattering experiment off a drop of the Big Bang. Okay, in a very real sense, these experiments make drops of the Big Bang. And this is the closest we'll ever come to studying them with a scattering experiment. But precisely because they are multi-scale probes like this, a jet is not just an electron. Decoding the information about the nature of the soup by looking at the modification of a jet is really quite challenging. And this is the challenge that many experimentalists and theorists are now occupied with. We need, skipping to the bottom bullet here, we need experimental evidence for the presence of point-like scatterers in the soup. So we need a high-resolution microscope trained upon a droplet of QGP. And this is the long-term goal of studying jets. And I will get to this at the very end. I'm going to take 10 minutes first to tell you where we are now. So jets don't make it easy. As I'll try to give you a sense of, I'll try to give you a sense of that. So theorists today are using data from experiments today to build up sort of the baseline of understanding of how these complex objects, jets, interact with this complex medium, the soup. And there are various theoretical frameworks for understanding this, and I'm going to show you results from only one framework. It's called the hybrid model, and I'm one of its authors. I'll give you lessons that are general, but the framework I use will only be one of those available. So what is this hybrid approach? So there are some approaches where you do everything with perturbative QCD, and there are other approaches where you do everything with the strongly coupled methods that work in the cousins of QCD when you have a dual gravitational description. And the hybrid approach is one where you mix the two. And the logic is that the hard scattering that makes a jet, that's perturbative. The first few splittings where this one parton splits to 2 and then 3 and then 4, that's perturbative. But each of these partons, as it propagates through the soup, is being tickled by lots and lots and lots of soft interactions with the soup. That's non-perturbative. And so we think of each part, we take a parton shower from Pythia, which is a standard Monte Carlo tool for describing perturbative QCD jets. And we go inside Pythia, and every parton in the shower, we say it's losing energy by propagating through the soup. And what is its dEdx? Well, we take that from a strongly coupled calculation. I was going to walk you through the logic of how to think about ADS-CFT and these strongly coupled calculations and how string theory is helping us understand how jets go through the soup. I think I have to skip this. The message is that a very, very complex quantum field theory problem in the context of this cousin of QCD becomes a geometry problem in a curved space-time background. And from that geometry problem, you get an analytic result for dEdx. So dEdx is given by an analytic expression, quite simple, in terms of a thermalization length. So this, in the cousin of QCD, this high-energy quark goes through the soup for this long. That thermalization length depends on the energy of the initial quark, and it depends on the temperature of the soup with some funny powers. And then there's a parameter here, kappa. So at the end of the day, in this hybrid model, we have jets from perturbative QCD tuned to describe nature in collisions of elementary particles, which we want to study how they interact with the soup, and we've done that by doctoring the jets in the Monte Carlo by saying every branch of this tree loses energy according to this formula, which has one free parameter in it. So we have to fit that one free parameter. And what I'm going to do now is I'm going to give you a sense of the quality of the agreement between this crazy model, because it's a model which glues together things from different theoretical frameworks. It has one free parameter, and on all the plots, I'm going to show you data versus the predictions of the model, and I'm not going to tell you what the experimental observables are, because this is not a colloquium on how to what you can measure with jets. But this is not a prediction, this is a fit. We take this one data point and use the value of this experimentally measured point to fit that one parameter, and then no more fitting. So everything else is prediction. This was post-diction. This was data that was available when we invented this model about 5 years ago now. And you fit that one parameter, and it corresponds, this is the value of the fit parameter. It corresponds to a stopping length in QCD that's about 3 to 4 times longer than the stopping length in the cousin of QCD. And that cousin is called n equals 4 super Yang-Mills theory and has many more degrees of freedom, so this is actually about what you would have expected. So that's pretty good. You look at that data and those pink bands, and it kind of looks reasonable. And then we made predictions. We stuck our necks out. We wrote a paper with a whole host of predictions before the experiments were out. And then in 2016, the experimentalists tried to chop our heads off. The slides I'm going to show you are from a talk at a conference in 2016. And on all these slides, and they're going to go by quickly, the sort of, unfortunately, they made our theory prediction green. The experimental data points are black with pink systematic error bars. So you look at green is us. The other colored bands are other people's theory, which I'm not telling you about. So green does pretty well. Different observable. 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 Green does pretty well, and that was it. So we were incredibly happy. And what this says is that parton energy loss is important. It affects many observables. And it controls, there are many observables that are controlled by how much energy the partons lose. And our model did pretty well on observables that are controlled by how much energy the partons lose. So this is great. We were, of course, very happy. But this brings us no closer to answering the fundamental question than we were before, because this is not telling us about the microscopic structure of QGP. It's telling us about how much angle. And that means we have to look at modifications to the shape of jets. So the first thing we'll do is we'll try and see how our very simple, I called it crazy a minute ago, model does. And I'm going to have to skip some things here because I want to get to the thing I want to get to. But so ultimately our goal is to use the scattering of partons in the jet to look for the hard particles in the soup. So let's think about how we might do that, and let's think back to Rutherford. So Rutherford shot particles at an object that he wanted to study. It was an atom in his case, and the particles were alpha particles. But he thought that atoms might be made of jelly. And if atoms were made of jelly, which was his expectation, then the alpha particles should not have scattered by very large angles. And in fact, Rutherford's original expectation was a Gaussian distribution of scattering angles with a fairly narrow width. Instead, as you all know, once in a while he saw large angle scattering, and that's how he discovered the nucleus. So what we're doing is the analog, or trying to do is the analog. But first, before we look for any large angle scattering, there should be a Gaussian distribution of kicks, because this liquid, as you plow through it, even if you don't see hard scattering, it should give you soft momentum transfer. There should be a Gaussian distribution of kicks. And so we're going to look for that first, and we'll do it by looking for broadening of the jets. Seems reasonable, right? I've got a spray of particles. They're all getting softly kicked. It should get a little wider. And now the complication of jets comes in. There are two confounding effects that you have to deal with before you can even see the Gaussian distribution. One of them is that jets themselves have multiple widths. A jet with 100 GeV can be this wide, or this wide, or this wide. And it turns out that the skinnier jets lose less energy. We calculated this in our way with the holographic dual description using the cousin of Qcd. Other folks, like Miliano and Zapp, calculated this in traditional perturbative Qcd just using quantum field theory. In their case, it's because it's actually quite straightforward. A wide jet has more particles in it, and so it loses more energy. It's as simple as that. Okay, and now you have to know that high energy jets are very rare. Jets are rarer and rarer and rarer at higher energies. And the combination of the fact that high energy jets are very rare and skinny jets lose less energy means that if you take 1 billion jets and put them through the plasma, the ones that survive at a given energy will be the skinny ones. The fat ones lose lots of energy. They get kicked down in energy. And then, because they came from higher energy where there are very few jets, they don't contribute significantly at lower energy. So because of this selection effect, this selection bias, when you measure jets at a given energy after propagating through the plasma, they actually get skinnier. It's not that one jet gets skinnier, it's that the wide jets in the ensemble get kicked out of the ensemble, or kicked down in the ensemble. So we then did a calculation in our hybrid model where we cranked up the width of the Gaussian that describes these soft kicks, and we were expecting to see jets get wider as you kick them more. So k equals 100 means you're kicking them a lot, k equals 0, no kicks. And instead, this is the angular distribution of energy in the jet in lead-lead collisions divided by the angular distribution of energy in the jet in proton-proton collisions. This is the center of the jet. This is 0.25 radians, and the jets are getting skinnier. So we're kicking them hard, but they're getting skinnier, and the reason for that is that this selection effect that I described. So that's annoying. We then did more work to propose a more sophisticated observable to look for the kicks, which I'm going to skip. And we then realized that there's another confounding, annoying effect, which turns out actually to be profound as well as annoying. And that is, I've been telling you, this jet propagating through the plasma is losing energy. Well, of course, it's losing momentum also. And energy and momentum are conserved. It has to go somewhere. Where is it going to go? Well, the soup gets momentum. So this jet lost momentum. That means I have flowing soup. Now, flowing soup at the end of the day turns into particles. And some of those particles will end up in what the experimentalist calls a jet. So the second confounding effect is that when an experimentalist measures a jet, it's not the same as what a theorist calls a jet. Because some of what's in an experimentalist jet is actually the flowing soup. And so we tried to model that. And I am out of time, so I will not tell you how we did, except to say that it's difficult. But you can see that we get closer to this data, but we're still not hitting it. And we then figured out what we were missing. And I'm going to skip this, although it's actually, well, it's hard for me to skip, but I'll skip it because I want to get to Francesco's work. The ulterior motive in what I'm choosing to skip is that I want to get to Francesco's work. So before we can get to Francesco's work, you really have to understand these confounding effects, which I didn't have time to tell you. But now we'll get to Francesco, right here. So there's a long road ahead, which I didn't have time to tell you all of. There are two confounding but interesting effects, both of which are large, that have to be understood first before you can do what I said is our ultimate goal. And so the goal is not a goal for tomorrow, it's for the 2020s. The goal is to look for large angle scatterings caused by the presence of quark-gluon quasiparticles in the soup. And Francesco, with co-authors, is the person who first figured out, made the first steps towards understanding how to do this in 2012. And he and I and Yi Yin are completing a paper in 2018, and we're definitely going to finish it in 2018. But I did not put a month. And we're going to answer how improbable are scatterings like this. In 2011, 2012, we computed the probability that an infinite energy parton picks up a certain amount of transverse momentum from a scattering. But infinite energy, add a bit of transverse momentum, that's zero angle. Now what we're doing is calculating the probability that I have a parton coming in with momentum pi, goes through a brick of plasma. So this is not yet a heavy ion collision, it's a brick of plasma, scatters, comes out as a parton with momentum pf after scattering by an angle theta. And this green here, this is Rutherford's original expectation before he saw the nuclei. This is what you would get with a liquid that's a liquid on all scales. This is a probability distribution on a log scale, and this is a Gaussian with a width that we estimated. And this, depending on assumptions about the kinematics of the value of this PF, these are the Rutherford tail. These are the large angle scatterings that you get because inside this soup, if you can probe it at short distance scales, there are indeed quarks and gluon particles. So this is what experimentalists need to look for and not just this. And so these large kicks are rare but not exponentially so, although this is a log scale. And so that's where we're going. This calculation from Francesco and me and Yi is merely illustrative. It's a brick of plasma. We now need to give this calculation after we finish the paper. We have to give it to people who do Monte Carlo studies. And they need to take that calculation and put it into a calculation of real jets in real collisions and look at how the scattering of the partons by those angles within a jet affects various different observables, including jet substructure observables. And if you have two jets back to back, you can look for kicks to the angle of one of them. All of this is ahead, and the data is coming in the early 2020s. And so to summarize the third of my talk, parton energy is of central interest. Parton energy loss, excuse me, is of central interest, and that we're doing very well at understanding. Ditto for how the medium responds, although I had to skip it, this flowing wake in the plasma, the moving plasma, is actually now an object of study, and that is interesting in its own right, because it gives us a handle to study how the medium responds when you shock it. And that gives us a handle actually on the question of equilibration, which has been very hard to get a handle on experimentally. All of this are prerequisites to studying the inner workings of QGP. There's a lot of work still to be done to go from Francesco's illustrative calculations toward defining, calculating, and ultimately measuring observables that focus on events in which, let's say, a 20 GeV parton in a jet scatters by 20 degrees. So the long view then, we are making progress on answering two versions of the emerge question. How does the liquid emerge as a function of time? By studying how you equilibrate and form, in effect, new quark-gluon plasma after you dump energy into it. As a jet passes through it, it kicks the plasma, which then has to reform into new plasma. And that actually will give us an experimental access to the how plasma forms question in an unexpected way. And then the how does the liquid emerge as you take your microscope and go to longer and longer and longer length scales. Francesco's calculation is the first step towards that, but there is a road ahead which I've tried to sketch. We sort of have a sense of the steps that are needed. Each one of these steps will need an interplay between theory and experiment. The theorists are working hard, so are the experimentalists, and I think this is something that will clarify when there's high luminosity measurements at the LHC in the early 2020s, and when there is a new jet detector at RIC called S-Phoenix, which is also going to be running in that case, 2023. So the doping and mapping the phase diagram, the experiments are coming in 2019, 20, and 21, and the studying its inner structure is coming in the early 2020s, and I encourage you to see how it all turns out. Thank you.
So thank you very much, Rajagopal, for this very broad view about this improperly called quark-gluon plasma. But now if you have questions, please.
And there's Andrea. Andrea, I mentioned the 800-person conference. He organized it, so he deserves a vacation right about now. But anyway, the conference in Venezia, for me it was a week in Venezia. For him, my goodness.
Going back to the first part of your talk, so the behavior of fluctuation around the critical point.
Yes.
I was wondering if there is an intuitive way to understand why it's positive and then the colors. I remember blue and red colors. And I've never seen that before. So.
Okay, so there's an intuitive way to understand why you get fluctuations whose magnitude grows near the critical point. I don't think the sign is intuitive. It comes out of Ising model calculations that are reliable, but I would not call them intuitive. But let me give the intuition for why the magnitude grows. So at a second order phase transition, the order parameter fluctuates. That's the essence of a second order phase transition, and it fluctuates on long length scales. And the order parameter in this case is actually a linear combination of baryon number itself and the chiral order parameter. And so baryon number is fluctuating because of what I just said, but also when the chiral order parameter fluctuates, you can think of that as fluctuations in the baryon mass. And so then when you have thermal freeze out, if baryons are a little lighter, you make more of them. If baryons are a little heavier, you make less of them. So in both cases, you get large fluctuations in number of protons, number of neutrons. You can't see the neutrons, you look at the protons. And so there's an expectation for enhanced fluctuations. And then it turns out that now this is well established, but I will not say intuitive. It turns out that the higher you go in non-Gaussianity, the more sensitive the effects are. So The second moment of the distribution goes like correlation length squared. The third moment goes like correlation length to the 4.5. The fourth moment goes like correlation length to the 7th power. The fifth moment would be whatever add 2.5 more, 9.5. You stop when as far as the experimentalists have shown that they can measure fourth moments of this distribution. And so theoretically speaking, you'd love to go to sixth or eighth moments. So higher moments become more sensitive to the critical fluctuations. And the sign comes because in the Ising model itself, if you think of the Ising model diagram, depending on whether you're on, if the critical point is here at the end of my thumb, this is the first order line. If you go away from the critical point in any direction, the second moment grows. But if you go in these directions, the fourth moment grows positively. If you go in these directions, the fourth moment grows in magnitude, but negatively. And I don't have an intuition for that. But I don't have an intuition, other than the fact that it's what happens in the Ising model. And this is all from the mid-2000s, mostly by Misha Stefanov.
You mentioned repeatedly that we cannot take the droplet of liquid and
bring it to Stanford.
Slack.
Yes.
Can we envisage one day of having experimental conditions in which you probe the droplet with lepton probes through different?
Yes. Oh, that's kind of. Are you thinking of what I told you at coffee? You make electrons and muons. I don't think we'll ever do neutrinos. But when you do a collision like this, you make electrons and muons also. I mean, anything that makes electrons and muons is down by a 1 over 137 squared. But you make electrons and muons also. And in particular, as I mentioned at coffee, one of the results at his conference, which I think was a complete surprise, at least to me, is di-muon events. So the muons, you have a muon pair back to back, mu plus, mu minus. And this was a measurement from Atlas. And Atlas compared how back-to-back are they. So so back-to-back means 180 degrees, but I want to call that 0. So I want to look at angle relative to that 180. How much is this muon deviated from being back-to-back? You look at the distribution of that angle in peripheral collisions where the nuclei almost miss, and then in head-on collisions. And in the head-on collisions, that distribution is wider by about 0.005 radians, which is about 0.3 degrees. So it's a small effect. It would be great for it to be measured by a different collaboration also, because it's quite a small effect. But if it's true, it's a sign of muons scattering as they go through the plasma. That means they're only interacting electromagnetically, because muons don't interact with the strong forces. And so that is almost certainly, if it's not an experimental artifact, if it's real, it's almost certainly a single scattering of a muon off of something in the plasma by a small angle. And that would be, I think, very exciting. I didn't put it in the colloquium because I would love to see it confirmed by another experiment. It's a small effect, and it was much discussed at the conference. Is that fair?
Just a curiosity, how much remains of the original idea of Toft of confinement in terms of condensation of color monopoles in view of these results?
Well, so there's a very creative theoretical physicist named Edward Shuryak, who actually is the one who, around the time when he was a graduate student, he's the one who invented the name quark-gluon plasma, I think in 1980. He's a professor at Stony Brook. He's been there for many, many years. And he has a long series of papers in which he tries to model the quark-gluon plasma just above TC as a soup of monopoles, of monopoles in the 't Hooft sense. So the answer is that many people, there are many people who still pursue that line of thinking. It's not quite clear to me how to control those analyses in any systematic way. So I don't include it in a colloquium, but it's certainly something which people are still thinking about.
Thank you. No question? Okay, so let's thank the speaker again.
Thank you.